So the principal investigator, once a proposal has been granted, needs to do what's called user work submittal, and then this will be internally reviewed, and then with that, the proposal as such is ready to go, but the participants themselves also need to do individual paperwork. Each needs to be registered, needs to have a domain account ready, which includes a personalized username and password. So I'm showing you this because in our experience, sometimes these steps get overlooked, and then folks ask, well, when can I get on the system? Well, the answer is look at your email from our user office, where you will have received various notifications. So act on these. So these are the administrative requirements. Once you have these fulfilled, then you also need the technical requirements on your side. Since you're doing remote access, you need a terminal application that provides SSH access that is built in for Mac and Linux systems. On Windows, you can use any of the ones that I listed here: Cygwin, Putty, MobaXterm. In most recent years got quite more uptake. So these are for terminal applications. If you want graphical access, you need on your system also an X11 server, or you can use what's called a VNC, virtual networking computing. This is a type of remote access interface. Yeah, and then what I have bolded here, in order to use this system, Carbon, your users, or you, need basic Unix or Linux command line experience. You need to know what the directory structure is, the basic directory structure for your home directory. You need to be able to navigate there with cd, ls, and you need to be able to edit small text files on the system. These are requirements as they have been for HPC access for all its existence, basically. There are efforts on the way to transition away from the direct command line access and make it possible for you to submit, to construct jobs, workloads in graphical user interfaces, submit from there, and then monitor, manage them, and then once they are done, get the results remotely back into them. But, well, such graphical interfaces are only available for high-profile licensed applications, or for things that we are working on. You may hear a little bit later on a couple of those. As far as AI and ML is concerned, that is an area that has seen tremendous growth over the last 5 to 10 years. Over the classical applications of HPC, which involved kind of heavy number crunching. Those heavy number crunching aspects are still present, still needed for AI ML. They are just underneath the surface. So in order to leverage AI and ML for these applications, as you will hear later today, developing force fields and things like that, you still need underneath these high-powered applications, and you need to have them properly configured. And that's why I emphasize here the need for command line experience to set things up correctly. Okay. So on the system, we have currently CentOS 7 and 8. And of course, we'll continue with this version 9. The system that manages batch jobs is Torque, and based on the MOAB scheduler. A lot of you will be familiar with this. We have Fortran and C compilers from various vendors, and to leverage parallel computing, both within the node and node to node. We have MPI, various flavors, and of course we have various libraries that come nowadays with the system software, plus LAPOC classical packages. The Intel MKL nowadays is also available. And incidentally, there has been a nice change in licensing terms for the MKL that is now available to use without cost. You still need to agree to licensing terms, but it's available to use without cost, even say at your home system for development there. You might find this helpful when you develop code. So now, in terms of application software, we have on Carbon a lot of project-specific code. I listed a few here. Quantum chemistry applications, density functional applications, nanophotonics, also big deal. I showed numerical, that is one of the key license applications. This, however, is available only for R1 employees. So some of the applications shown here are accessible for employees only, unfortunately, as commercial licenses go. And by employees, I mean people affiliated with Argonne. With AI, of course, nowadays you have to deal a lot with data processing and visualization. So Python is available on the system, both from the system side, and a lot of users will need their own constellation of packages, and for that users typically install or download Conda and install one of these systems, mini Conda and so on, which comes with some visualization packages as well. We have the big commercial ones, MATLAB, Mathematica as well. Well, COMSOL, numerical, they really should be actually on the top item here under project applications. GNU-plot is, of course, available for quick and easy visualization. And image processing, we have ImageMagick there. So you can do a lot of things on the system with standard software. The means to access these software is by environment modules. That is shown in detail on our wiki. In order to locate details on the system, you find a link here. So that is really important, wiki.anl.gov/CNM/HPC. You can open this link, and now the trick is how to get to it. Oh well.
We are still looking at your.
Yeah, yes, okay. I know. Good. So here we have main page. So if you want to know, for instance, how to use VASP, you go up here in the search page, search for VASP, and you click on it, and there you go. So VASP, like others, is subject to licensing, so you need to first request access. And then, as I hinted, let's make this a little bigger even. You need to choose which version you want, major version, minor version. And this is done like on other HPC systems by loading an environment module. You can do this on a command line or add it to your bash or C file. This is where the ability of using a text editor will come in handy. And then you see various binaries are available. So VASP is a curious package in that respect, that it comes with different different binaries for various application options. So these days, people will use VASP 5 and VASP 6. So here's all the information you see about choosing the correct binary. For another example, let's see. Well, yeah, numerical, for instance, for one of those commercial applications. Also, there are detailed instructions here. And I'm choosing this example because it shows different ways of running a GUI application. You can run a GUI application on your system, or you run it on Carbon, show it remotely over X11, or you use VNC, which is this virtual networking computing. So this page will show you how to do these various setup items. One thing that also comes in will be needed is license access. And again, this is for people affiliated with Algorand, so not necessarily external users. So for that, you need to go into your SSH application and actually modify, tell your SSH application to forward specific ports on the network so that you can use them remotely on your system. Again, details of this are shown on the wiki. I don't think it will be helpful to go into this here in detail. Subbu, what do you think?
Yeah, no, I mean, I think users can reach out to you if they want more details.
Yes. Yes. Just an example for some of the basic ways of accessing the system. You'll access our login nodes from inside Algorand. You can access them directly from offsite. You will have to go through our SSH gateway. That is a step that may be new to external users. Instructions again are on the wiki here on this link here under network access. Here. So there you are. You see again what the requirements are. You'll find instructions how to set up your system to access the SSH gateway, and also how to set up remote graphics access. So I don't think it will be helpful to get into any particular details of this here, just not enough time. Normally, this is a matter of longer part of a course. So once you are on the login nodes, you can then compose your PBS jobs, submit them, and usually you'll get an email once the job is done. After that, you access the, you can inspect the results from the job. And let's see, there is, so you transfer the files back to your own system. That is what, and you can visualize them there. And another nifty way of doing things is, well, just inspecting the files directly. Let's see if I can show you an example for that. Typically, an application will create an output file and an error file. For instance, let's see, an output. Just use an application to inspect the text. Now, if your application has an error, then the job script will create an error file. And this is the kind of information that you will need to tell us if you request support. So let me show you briefly how that works. How to request support. So again, the wiki here has an HPC support entry. So in order to request support, you submit a support request using this link. So this will go to our site-wide support request system. You will have to log in for that, and then you can construct a specific support request. For instance, here you can choose type, whether you have difficulties with remote access or how to begin, or if you have trouble with a PBS job. And for PBS job here, various fields are required. The most important one, often overlooked, is the precise error message. So you fill in the data and then you submit the request up here. You can also submit by email, in which case the required forms are needed in the body of that email. And again, for all issues, you do need to include the exact error message that you got. And of course, you need to tell us the command that you were using. And for PBS jobs, the working directory, very important. Which file was the one that you used to submit the job, and say which job number things occurred on. Often, to take a step back, if you have difficulty accessing the system in the first place, then you need to tell us various aspects of your networking setup. Without this, getting the answer to you will be a little more involved, because we have to ask back, okay, what is the error message, which directory did it occur to, or what host are you logging in from, what directory are you in, and so on. So make sure you include these items in your initial report. Okay. I think this just about covers it for basic usage. Oh yeah, let me highlight one other aspect. recall that I mentioned the importance of familiarity with Linux. If you are new to Linux, I put together a little page here, documentation from beginner to advanced usage. So have a look at this. There are various guides available for various levels, beginners, intermediate, and advanced. A book will be very useful because if all you do is you Google something on the web, well, you get a lot of content that isn't typically organized or targeted towards teaching, but rather just a list of commands or just a short item to work on. Whereas if you get an actual book, then this will be created for teaching and something that you can follow. Okay, with this, I think this just about covers it. So, oh yeah, and just to take us out here, I want to show you a little example here. If you have a data file on the system, you don't necessarily need to put up a graphical analysis application. You can plot things on the command line with an application like GNU-plot. You just tell it to set the terminal to be like a plain dumb terminal, and then you can do things like plot nanoscience in the terminal. So this is pretty old school, but for quick and easy access to data, this is simple enough, and you'll see if the application is doing the right thing. With a bit more tooling, once you get familiar with this, you can even do things like, well, movies this way. So I found this quite helpful in a project that I've been recently working on. So just as a little example here. So this tool that I'm using here is called PL. That's something that I wrote myself quite a number of years ago. But you can use GNU-plot to GNU-plot command line facilities to familiarize yourself with this. Okay, I think that's about it. If you've got questions, let us know. Let your scientific contact know, and precisely describe what your question is. Okay, Subbu.
Thank you so much, Michael.
Yep.
Any questions for Michael? You have time, so if you can drop your questions in the chat, and Michael can actually answer those for you. So as and when questions come, because all of the tools and softwares that will be discussed today can be you can operate them by logging into the Carbon cluster. So if you have any questions on any aspects of, like, whether you want access to the Carbon cluster or any other details, Michael maintains a wiki page, as he pointed out, that you can actually look at once you are a user. And if you have any questions, just feel free to actually put them in the chat, and Michael can answer them during the break or even later. Feel free to email him as well. All right, thank you so much, Michael. So next we move on. So next we move on to Aditya, who is actually going to talk about a multi-fidelity scale bridging framework called BLAST.
Hello everyone. Is my screen visible?
Yes, it is. You just need to put it in a.
Yep.
Yep.
Okay. Good morning, everyone. This is Aditya, student of Dr. Subbu, and I am today going to present on the force fields in general, the BLAST framework, which we have developed at CNM, Uh, to begin with, like I would like to lay my emphasis on like why do we need to generate force fields, like where we use them, etc., and then go over a general recipe which would help us in developing or parameterizing the existing force field forms. And then we'll go through a working example or a recent parameterization, which would like help you understand what BLAST is about and how do we visualize our end parameters and compare properties, etc. So to begin with, like I presume there might be some experimental folks which might need an introduction to where we use force fields and what the force fields are. I would begin the talk with that. And then as we develop, we would go into the recipe of the BLAST framework. Okay. So one of the applications which everyone might be quite familiar is the phase transition between two phases of, say, two solid materials here. The black one you're seeing is 2D black phosphorine, and then this is the blue phosphorine. Having a proper parameterization which can like model these two minimas, like these two structures well, can actually tell us on what temperature conditions or what strain conditions are necessary in order for the transition to take place. That's one of the models which we have built using BLAST on 2D phosphorine. It's a test of parameterization. And then about the thermal transport, like any material around us, we would be generally interested in thermal transport, say it being a solar panel or even the electronics that we are using in. And these layered materials which have these niche properties around, like one of it is WSE2, where one of our group member has actually made a model or parameterized a test-of model for modeling the thermal transport. And the target properties are the quantum calculations, where we see that the model MLBOP does a fair prediction with the phonon and also the heat capacity. And owing to this accurate predictions, we could also expect the dynamics to be predicted very well. Another common application is like searching for new structures, or in fact, the metastable structures. So more details on like how this framework works, or like how this setup works, would be explained in the next talk on casting. But what I would like to speak on is, even to sample through the structural space, one would need a accurate model which would tell us like, hey, this structure is kind of different, or this structure is energetically different from what we already have. And that needs to be something really quick and also accurate. One could resort to techniques of quantum calculations, but then to be practical in our search processes where we have millions of combinations, it would be wise to have a accurate model, and that in that scenario too, we find these force fields to be very helpful. Then one another recent work that we have accomplished is force field for silica, which is quite well known and very well in our everyday lives. So there are about like 21 experimentally realized polymorphs of silica. And as you can see, like there are existing parameterizations, GAP, BKS, SHIC, PSO. These are like, if you see the predictions, these are the energetic ordering predictions, and the pink line, like the MLBKS is in here. Let me pull out the pointer. So this is the MLBKS prediction, which is closest to the experimental curve, the red curve. And this is like quite fast when compared to the gap parameterization. And we'll go about more details on this work as we are going through the recipe of BLAST. But the important thing is, like, since if as close as we are to the experimental predictions, we could like even employ this kind of model in finding structures similar to, like, here the example was for carbon. We could similarly employ this model to search for silica structures. There have been many hypothetical databases with structures, like millions of them, even to verify we would need an accurate model, and this is one which we have come up with to accomplish such a task. And the next one is on autonomous synthesis. Right now, we see there's a lot of moment in the autonomous synthesis platforms, like building up them. There'll be more details by Dr. Henry Chan in the noon. But if we try to think about a scenario where the bot needs to look at the properties of the materials before it even actually synthesizes it. Like, say, for example, you want to say, as depicted in the figure, you want to come up with a polymer electronic, and then there are two parts that the bot figures out, say part material A and material B. But then you might also have a constraint. Okay, is it biodegradable? Is it sustainable? And in those scenarios, you might actually use, if you have a good force field model, you could actually study the degradation pathway of material A and B and see which is taking up the least energy, or in terms of thermodynamics has the least free energy, to make it easy for degradation, which would be more compatible with the environment. So these are few applications where we use force fields or this classical molecular dynamic models in day-to-day applications. But I would also like to speak on different molecular modeling techniques available to us at different scales, and when do we choose them, and how. So to begin with, there are these Ab Initio molecular dynamic techniques where we have the atoms along with the electrons. So these are quite maybe up to a nanometer scale, and can handle a picoseconds based looking at the computational efficiency. And then the classical MD simulations, which we have talked about until now, about the other applications. Like here we see the growth of silicene on silver substrate. These can be up to 100 nanometers.
Is there a problem at my end, or is it Aditya?
I think his internet might have broken off.
Yeah. Sorry about that. I think he's going to rejoin. While we wait for Aditya, are there any questions for Michael or in general? All right, give us a minute. Henry, why don't you actually give a brief overview if Aditya has issues with? Okay, all right. Anyways, Aditya, you need to hurry up now.
Yeah. Okay. So, yeah, the point I was trying to make was like, okay. So looking at it's like all about like solving this force equation where we get the forces from this functional form V, and this is something what we have been referring to as force field or interatomic potential. And we have this several types of interatomic potential models. I have just named a few. Like if we look at this Lennard-Jones, the simplest form, we see epsilon and sigma. These are the two parameterizations. Two parameters needs to be figured out for a single elemental system. And similarly, TESOF would have about like 14 parameters and EAM about 22. So at the end of the day, it's like finding the right parameters, which would give you correct correlations or the interactions between the atoms, giving us some realistic predictions. So at the end, like when we think about this problem, it's all about like optimizing this right parameters to our set of target properties for a material system that we intend to. So typically, if you look at the force field development from the past, like talking about the life cycle in general, like it would have like taken a few years to come up with a force field. And then if there is, if it was targeted for certain properties, it's like say active mechanical properties or having basic energetic ordering correct, etc. That would be good. And then like if some of the people in the community tend to use it for other properties, like say thermal conductivity in case of having bad phonons, like it would like come up with a superficial result like after a certain number of years, but to realize that even the life cycle of it like is about like 4 to 7 years, which would make it difficult to iterate or like to accelerate the development of materials. But with the advent of the AI techniques and fast computers, we have this general workflow where we can quickly go over this cycle and then validate it and then refit to the parameters if necessary. So typically the first step is the model selection. Like say if you're interested in reactions, you go for reactive models or simple van der Waals effects, then you can go for some bond order models, etc. And for electrostatics, you can look at some Buckingham type of potentials. Once you select the model, then you'll be trying to prepare the training data correspondingly based on the target properties. it can be just the structural properties like lattice parameters, the energetics, or the elastic properties in case you're looking for mechanical property computations using your force field that you're going to develop. Once you're done with the training data, then you need to you need to evaluate every certain parameter set that your optimizer throws in and give a feedback to the optimizing algorithm. So in here, the objective evaluation can be like for a single objective, like say you're fitting only for one parameter and for one structure or one polymorphs, then you'll have a single objective. But typically we would want the force fields to span across different structures and different properties. In that scenario, you will be having multiple objectives, and we will talk about like a hierarchical system which was developed in this group, which actually is the key to faster development of force fields. And also the supervised learning, here we employ the reinforcement learning techniques, which actually takes in which actually throws in the parameter sets for each iteration of this parameterization process. Then once we have the set of parameters, we need to cross-validate them just to avoid, say, overfitting it to the same training data. We need to check some other properties or other structures, which will tell us if the parameterization is useful for, can be applied wide across the properties and structural space, or is it like limited. Then we tend to add more training data and repeat the process. So in this workflow, the user would be free to select the model and the style of object evaluation and the optimizer. Okay, so I would like to take through the steps of it by actually taking in a recent parameterization that we have employed. We have come up with this silica parameterization for BKS, Buckingham model. And typically to make use of this workflow, any user would need like Python, a basic understanding of Python and command line prompt, just like Michael was talking about, and LAMPS MD package. Currently we have the MD calculator we have is LAMPS within the BLAST framework. So step one, as we were talking, is about like model selection. For this case, we have actually chosen the BKS model for the silica. It's a pairwise model containing a Coulombic interaction and a van der Waals interaction. Now, if we consider the case of silica, we'll have typically 3 interactions: silicon-silicon, oxygen-oxygen, and silicon-oxygen. These amount to about 13 parameters. And if we take a quick peek at like what are, just give me a second to make sure. Okay. If you look at like what we have within the BLAST, we have something called as a model.json file, where we code in, you can think like this acts as a database for the parameters that we are trying to optimize. Here we have like each parameter listed for that certain type of interaction. And then we also have the bounds of the search. And typically we would also like have some conditions. For example, if we try to take a peek at the types of parameterizations, we do have like some conditions which need to be checked between the parameters while fitting, just to ensure that which don't meet certain physical constraints are not evaluated. This would save us a lot of time. So this is about the model, the first step. And then we'll come back to this post-validation. That is after the step 5 I was talking about before, where we need to cross-validate in order to prevent any overfitting. We'll talk about the case which occurred during this fitting process and how we tackled it. So next is like the training data development. Like for silica, there was this experimental data present, where we had these global features like say density and then the energetics, and the local features from the structure were extracted in the form of RDFs and ADFs, radial distribution functions and angular distribution functions. The idea we use in BLAST is like typically we have a AMPS data file. Like LAMMPS has a certain format for the geometry of atomic structure, and we add in the metadata where the properties which we intend to fit to are as commented lines, as you see. If we take a quick look at the training data, like this is typically, which is similar to a screenshot. This is how the LAMMPS data file looks. Like you will have one file, like for your single data point, you have all the properties listed in, and BLAST can like navigate through this file in order to pick up whatever parameters we are interested in. Say you want density, yes, from here, lattice parameters, cohesive energy, etc. And if at all the case has elastic constants and phonon dispersions, etc., those would also be listed in the same metadata. So this is the step of training data preparation. Once you have your training data, it's about like launching the run. For example, although we don't intend to like quickly go through and converge at the moment, all we need to do is like run our optimizer file, like which takes in like which goes through the model.json and picks up, okay, these are my upper bounds, or these are my lower bounds, and throws in a parameter set for evaluation. So MCTS, as I was telling, which I would be talking about, is one of the optimizers we have employed for global search. And you activate your Python environment, and then like you just start running this. This is as simple as we can do. And I'll go through like what happens through the fitting process. Like as the code is running, it's just to show that we just need to launch a single Python script in order to launch the fitting process. But what type of data we get and how do we analyze it is the next thing that we are going to talk about. So typically, once you have this training data set and you employ an optimizer like the Monte Carlo tree search in here, we have like say it throws in say parameter set 1, and that goes into the objective evaluation. And here, like based on the properties we target, we have them in several stages. Like each property is a single stage in this workflow, like say lattice parameters, cohesive, density, angle. Now, the advantage with having this hierarchical approach is, say you, as long as the parameterization reaches a space where in the parametric search space, in the high dimensional space, unless it reaches the first parameter, it wouldn't be able to like go in and optimize the next stage. So this way, it helps us to ensure whenever it's going to the next, say, cohesive energy state, or it's already in the parametric space where it already has good lattice parameters. In that way, at each level, we are like ensuring that the previously set constraints are taken care of. And also we are limiting the number of evaluations, because if at this stage there comes a parameter set which doesn't do good with these constraints, like say lattice parameter less than 3% error and cohesive energy is less than 10% error, we wouldn't go in to compute that parameter set. We would just reject it, because we already have a parameter set which is good in these two constraints, in these two properties, and we would only want the next one to be evaluated if it like is going through the first two parameters. That's a basic and necessary condition. Then we go on to evaluate and check how good it's in density predictions. This is just an example case, and the users are free to choose any order of the properties, and also any order of polymorphs. Like the structures can be ordered in whichever way the user would want to. Okay. And to give a brief on MCTS, and which would be covered in more detail with some benchmarking cases in the next talk, MCTS typically has 4 stages: selection, expansion, simulation, and backpropagation. So it would start with a node, like typically these work on a scoring system, which will be written by the objective evaluation function. Now, based on like the green things can be considered as the path chosen by the MCTS, and based on the scoring, like if it is suitable enough or if it is the lowest in this case, then that particular node would be picked up and corresponding steps like selection, expansion, and simulation are performed. So this actually works on on a selection policy, which has an exploration term, this and an exploitation term. This would ensure a fair trade-off based on the hyperparameter tuned C in order to like go through the paths of the tree, which might have a decent parameter set. So it can, in a brute force technique way, we can actually go through in a high dimensional space, go through and get random points and then try to figure out the range. But in this fair balancing of exploration and exploitation, this would help us in navigating through the search space. And we do have an additional term, which otherwise MCTS was proposed to be a discrete action space problem, meaning that the continuous surface energy, potential energy surfaces, problems like that would not be solvable because of its discrete nature, but adding an additional term helped us in applying it for the continuous space problems. More details on it would be definitely presented in the next talk. So if we go about and look at how we parameterize, so as the search started, we'll have something like the iterations spanning across time, and with the each evolving iteration, we would see the objective score in this case to drop down. So that is what we are typically expecting. And what this means is, like, for example, just to show you, like, if we look at the top 30 parameters, like this is some old example, but we would see that with the one bearing the lowest scores has actually reached all the targets that I have set. And I would see the status of each of the parameter set and its corresponding stage. Like say I targeted 21 structures with their energy ordering to be right, then this is something which would have happened. So, and also for the range we have set, upper bound and lower bound, we would be able to see in here like what's the maximum and minimum, that is our bounds, and also we would be able to see how much of the space has been explored. If we see a parameter like coming always closer, like most of the parameters, say 90% of the parameter sets end up closer to the upper bound, then it's an indication for us to say, okay, we need to expand the bound, like we need to expand the search space. So these things can be looked up via this interface. And for testing the force field, like typically, once you have got this stage, you would be interested in seeing how the properties look. So, for example, these are like PKS, gap, chick, PSO are some force fields which are already existing in the literature. Say we take the best and then like try to compare like how it does with our latest parameterization with the experimental. We see that MLBKS, the model in this work, was actually getting the energetic ordering much better when compared to the most accurate gap potential. And in this way, we can also like keep adding the parameter sets that we want to compare and have a look at different properties. Apart from this, we can also like have some comparisons like how each of the parameter set is varying. For example, I have some correlation plots on like how the error is correlated to the parameters. So these can be generated for a whole set of run, like across like one whole set of parameterization runs. Say you generated some 10,000 sets, and it actually can go through this analytics and figure out which parameter needs to be tuned or focused upon to get a better parameterization. So this is one of it. And while testing this model, like we have, apart from the training data where the density, energy, and the angular details were included, the tetrahedral and the intertetrahedral angles, we were like testing out how the force field would do on certain properties, like say elastic constants. We see the MLBK sits right on the top here, like with the this is the error matrix for each of the elastic constants, and we see it does good. And then we also look at the amorphous structures, and the structure factor seems to be in very good agreement with the experimental values plot. Now the issue was like when we have fitted this to the solid data, and then when we try to do it for predict the melting point of liquid, say, or do some high temperature simulation, the force field has failed. Before going to add some data and reparameterize, we wanted to understand why did it fail. So we quickly drew up some pairwise interaction curves between different interactions, and notice that the silicon-silicon interactions are actually accessing very lower interatomic distances, which led to the catastrophic failure of the model, because as we increase the temperature, the jiggling of the atoms would make it reach much closer interatomic distances. And to address this, this is what I was mentioning in the first model selection process. We have added a additional LJ term, WCA parameterization, where we just reject the attractive part of the model and then like add in the repulsive model. So then we just add additional 2 parameters. And since it was already, since the development or addition of model is like quite straightforward, we could go about and like optimize those 2 additional parameters, correct the interactions, and then when we looked at the liquid properties, we see that they are in very good agreement with the experiments. So this is one of the works, and this is how typically one would like go about using BLAST in general. Apart from this, like these are few notable works on like the 2D phosphorine case, which I was mentioning, and these are like about 54 elements across the periodic table fit for clusters. About 70,000 configurations were in this. You could look at the error bar and see most of them are having accuracies, very good accuracies. And one, we could like study the nucleation of ice, which was shown in the beginning, and tests of parameterization for a layered material, WSC2, and catalytic surface iridium oxide, and like different class, different dimensionality of gold using a hybrid bond order potential. These were few of the notable works from BLAST, and we are like currently working on different 2D material parameterizations like TERSOF, and we are about to come up with different parameterizations for silica. They should be available soon. So in conclusion, one, we are working towards, one quick thing which I would like to show you before is the report file. So as we are running the fitting, we would also come across, we have multiple outputs, certainly, a few which I have shown you across the Streamlit interface, but we do have this report file from which I am like post-processing the data, where each stage, like say for example, the lattice stage is computed, like the target predicted values and all are noted down, and also the score or the error criteria, all the data is in here. So we want to move from the text data to more like say tabular data or the data frames to go towards much deeper data analytics and in a way towards autonomy. And also the model library that I have shown, the .json file, which has the parameters. There should be different models coming up for reactive models, say ReactFF, or hybrid models like BKS plus LJ, which we had, or TERSOF plus LJ, which we already have. Currently, we have like Stillinger-Weber, EAM, LJ, TERSOF, and BKS, and souls, etc. parameterizations available in BLAST, but further additions are to be made. And also MD packages. Like currently we have the evaluator to be lamps. It would be good to have NAND and GROMACS under the hood because it would allow multiple users, mainly from the biomolecular side. Looking at NAND, it reminds me about some of my experience where once upon a time when I was working on membrane simulations, I would, I basically wanted to simulate a boron removal from water. But then advisor back then actually told me about this process of force field fitting. Like we need to go through these several stages. Back then I was not able to get the parameterization for the system I desired to simulate. But today with BLAST, I'm certainly confident that if you have something in your mind and with the generation of right training data, we do have a tool with which we can realize our or study our systems of interest. So also other part is the training data, which you have seen, the metadata, which was put in the geometry file of lamps. So using quantum techniques like WASP or even like maintaining a database which can collect from all the external material databases would make it more automatic, and users would be able to choose from the existing data or even be able to calculate the data for their material or their atomic structure of interest. And then to ease out all this, instead of running in the backend, currently we have something to visualize the data, but it would be also good to have a place where someone could just select the model and like in a plug and play way and using an interface, which I would show, but it's not functional at the moment. Having such an interface would ease out, and even any novice person in materials who is interested in getting the force field will be able to just put in the training data, select the model, and select the type of objective evaluation and go ahead with the parameterization. If anybody is interested in force field development for your material of interest, please do contact us. Here are our details. And if interested in using the package or HPC resources, do submit user proposals. And these are the scientific contacts, Dr. Henry Chan and Dr. Subbu. So I think we have still a couple of minutes. This is some user interface which we have. It's not functional at the moment, but this is on some lines which I would like you to think, which we will possess it in the near future. So with the login is the first thing, and then once you have access to it, you'll be having a task dashboard where you'll be allowed to create a new task. And in the task, we'll go through the similar steps, like make your training data, like add in the properties, add in the material ID, like this is corresponding to the material data, materials project. And then you can add in what properties need to be looked at, like what are your target properties. And then you can select the model. In this case, it's say test of, and then set the bounds of each of the parameter, and then select an optimization strategy. And then submit your task on a HPC. This was typically created to work on Carbon, but this is something which is to be pursued and made better. So yeah, this is all I have. Thank you. I'll be happy to take any questions.
Yeah, thank you so much, Aditya. So one thing which I do want to acknowledge is that Henry Chan, our scientific staff, is the principal developer for this BLAST framework. And if you have any wish list that Aditya went through some of his, please feel free to use that user survey, and you can actually let us know. And we will actually try to implement those in future versions of BLAST. So we're also working towards incorporating symbolic regression and give users more flexibility to actually just learn the physical forms of these interatomic potentials given a DFT or experimental training data. So there are all those additions that are actually going to happen. But if you have something else that you think is important for you, we can certainly actually put our effort towards incorporating that in BLAST. So any questions that you have on the force field? as I said earlier, please feel free to put it in the chat or reach out to any of us, and we'll be happy to actually answer questions on the capabilities and how it can be actually applied to your specific problem. All right, then in the interest of time, let us actually move on to the next tool that is basically on structure optimization. And Suvo is actually going to talk about casting, which is a continuous actions-based research for inverse design. So Suvo?
Yeah. Is my screen visible?
Yes, it is visible,
okay.
and it looks great.
Okay, just a second. Hello everyone, and thank you, Professor, for the introduction. So I am Subo. So I am a visiting grad student at Argonne National Lab, and I am also doing my PhD at University of Illinois Chicago in mechanical engineering. But my research mostly focuses on inverse design of material. And today I'm going to talk about my recent work, or rather a large portion of my PhD, that is developing this tool for inverse design, which we call casting. Basically, it's an abbreviation for continuous actions-based research for inverse design. Just to start with, right, I understand there are many experimental folks here, right, who are not very much familiar with the computational techniques that we use, right? So I just wanted to give you a brief heads up on how the computational design and discovery work, right? The first and main principal component of any computational design and discovery is the data, right? So those of you who know, there are these known databases such as Materials Project, AFlowlib, ICSD databases. These databases, people are doing experiments. They are predicting new materials with some theoretical modeling, and each and every year, tons of data are being deposited in these databases, right? And these data are perhaps the most important part, because nowadays we understand, right, a lot of effort has been given into AI, ML, artificial intelligence or machine learning driven materials discovery, and these data are basically the key aspect of them. The second part, right, if you are trying to do any design and discovery with any machine learning models, right, you need a representation. So basically the representation should be a scalar representation or some quantitative representation of these materials that this machine learning model are going to see, right? The key aspect of this representation that you must have, right, they should be invariant to the permutational. So you having a chemical compositional space, right, and your represent should reflect the permutational invariance or rotational or translational invariance, right? Basically your machine learning model is seeing this representation, right? And for an example, say you have a crystal structure, right? And you just translate that crystal structure. Say you add some value to their Cartesian coordinate. It remains the same crystal structure. But if your representation is not respond to that changes and understand that these are two similar crystal structure, ultimately your machine learning model is not going to learn anything, or whatever it will learn, that will not be very helpful. The next thing is the model itself, right? And if you just go to the Google or any publication sites such as Google Scholar, you type AI ML in inverse design, you will find there have been application of tons of different model. I tried to highlight a few different model that are most recently being used. Those are basically graph neural network based model. So if you follow these papers, right, you will find this model. So these are particularly accurate in predicting materials property from their crystal structure using a graph-based architecture. The final part is the design and discovery, right? Now you have all the component, you have your model, you have your data, and you have your representation. So you can just use this model, right? You can train them. Either you use them as a surrogate to predict some materials property, or you use those model to do the inverse design. You know the property and you try to predict the crystal structure. But if you notice carefully, right, most of this design and discovery are one key aspect, you need this data, and the generating data is a must. So predicting crystal structure, like I said, the data will be the crystal structure, and from us, computational material scientists, so we basically looked at it basically as crystal structure prediction. We imply some algorithm, which are basically optimization algorithm, and we try to find different crystal structure that are sort of theoretically stable. Like if you use some high fidelity model, say quantum calculation, right? If those materials are stable, we call them as either metastable or stable. Now, I talked about a little bit on optimizers, right? So optimizers and the crystal structure prediction, for the crystal structure prediction, right? You will have a surface. It's a continuous problem, right? What do I mean by continuous? For any optimization problem in general, if you try to plot the function against the variable, so this is a short 2D representation just for the understanding, but you will see a surface like this where you will have this minimas, right? From the aspect of materials, right, this particular minimas might be very interesting because they represent local metastable states. And these metastable states, right, they are not usually accessible in your regular thermodynamic condition, because the barrier is much higher than the general thermal barrier at current thermodynamic conditions. So like at time scales of atomistic simulation, you might getting this minimas are basically a rare event. And the problem is kind of continuous in nature, because if you imagine, right, so basically like if you have a crystal structure and you perturb it atoms a little bit, so it's a different structure now, or but how do you perturb? You don't have a discrete grid-like option, right? Like, hey, so my atom can move from one place to another place, which are predefined. You can move it very smoothly with any deviation. So this gives you a continuous space, right, where crystal atoms are freely able to move and change and hop around this minimas to give you different metastable configuration. This makes this problem particularly challenging, because now you have a infinite amount of possibilities that you can sort of have. Okay, now I was talking about the continuous space, right? If you the other aspect of it's a rather similar but a more simplified version, that is discrete action space. I try to elucidate one example of my work that I did on the defects on this MOS2 surface, right? So you have like molybdenum disulfide, and on top of that you have these sulfur vacancies, right? And these sulfur vacancies can migrate, and the alignment of the sulfur vacancies would give you some phase transition in MOS2, right? Like 2H to 1T, like basically semiconductor metal transition. And those are particularly is of interest in electronic applications. Now, if you look at this problem, right, isn't it a rather simpler problem? Because you see like the defects can move on the lattice. You have like discrete spots, right? So the possibilities are finite and it's comparatively easier to optimize, right? Now the thing is, right, all of the problem regarding crystal structure prediction that I talked about so far, they need an optimizer. And it's not like we are the first one trying to develop such optimizer. People have been using this optimizer for over a few decades, and I would rather say quite successfully, right? And like I try to put a general overview of whatever optimizer people are using. Like you can broadly, like the popular ones are basically meta-heuristics based, like the evolutionary algorithms, and the swarm based, like genetic algorithm or particle swarm. Then there are a little bit, I would say like a decade back, people were more inclined towards this random and probabilistic type of approaches, right? Or Monte Carlo sampling based approaches, such as like simulated annealing or minima hopping or Bayesian hopping, right? These were good, and people have predicted a lot of different phases of new materials, right? But like as we moving towards an era of AI, right, where like you are trying to like increase your boundaries, right? And the boundaries, I mean, you are trying to develop complex and more hard to predict material that are of larger sizes and high dimensionality, where this algorithm in those applications, right, this algorithm sort of struggles struggles in the sense, so these algorithms are basically like basically reward based, right? So if you set a fixed target objective, for an example, you take genetic algorithm, right? You set a target objective, right? And when your genetic algorithm, those who are familiar with genetic algorithm, they know, right? You have generation, and so each generation progresses to the next by doing some crossover mutation and sort of generate new candidates in your population, right? And the processes are directed by the reward, right? Like say you do an operation, if it gives you a better value of your objective function, then you choose that. This is helpful for most of the cases, but for some cases this can be problematic, right? For an example, I try to show you an example of defects, right? This is a study I did. It was published in ACS Applied Materials around 2 years back. So like the MOS2 example, right, is the similar example of MOS2, right? So for the MOS2, if you are trying to optimize the position of the defects, right, to get a most favorable condition, right, the challenge here is, right, like when you try to align this defect sequentially, right, and we know the solution, the most favorable condition is the line defect. But when you start from one defect, right, you put another one in a straight line, your objective, which is basically energy, there is a barrier. It usually increases, right? And then suddenly after say 8 or 9 defects, it suddenly jumps down. So this barrier, right, if you can imagine, if your objective function, like if your search algorithm is purely entirely guided by this barrier, right, it would initially it would try to align the vacancies in a linear fashion. It will see like it's not giving a good objective, and it will abandon, which will result in no convergence at all, which was a problem on another publication that my work was inspired from. So they used GA. This publication is also from our group. They used GA, but GA ultimately didn't converge. Another set of problem with this evolutionary or meta-heuristic based algorithm, right? Like once you go to higher dimensionality, right, they sort of tend to struggle a little bit on scaling. Which is, I would say, problem because like as I mentioned, right, we are trying to expand our boundaries, and in higher dimension the possibilities increases at like exponential pace, right? So these are two basic challenges, right, kind of what I'm highlighting, and these were sort of our motivation in going towards something that is like more scalable at higher dimensionalities. So we try to look at approaches, right? Those are policy based. A former postdoc in our group, Dr. Troy Loeffler, right? So he was inspired from this Monte Carlo tree search, right? So it was first implemented, I mean, Monte Carlo tree search was around for a long time, but it was like one of the notable implementation is Google AlphaGo game, right? Where it was used to, with the conjunction with a policy-based network, right? The Monte Carlo tree search was implemented to play the games, right? And this AlphaGo network, right, it managed to beat the world best player on the Go board game, which was remarkable at that time, right? Later onwards, there are better versions of it, but the fundamental application lies on this implementing Monte Carlo tree search, right? But as you notice, right, this is the board game is a like discrete action space problem. Like you have like finite places in the board where you're sort of, you can move the pieces around, right? And our problem that we are trying to deal with is more continuous in nature. So like modifications are essential. Before going into the modification, right, what we have done, I would just like to show you like the MCTS at present days, the Monte Carlo research has been being applied to many different domains of problem, right? You have like board games, even in material science, you have for defects, polymers, grain boundaries. If you notice, I have all mentioned like these are all discrete problems, right? Most of them are discrete problems. Then you have like some real life application, traveling salesmen, unmanned air vehicles, the signals, right? Now coming back to the question, right? Like we are trying to take the MCTS that was working very well in the discrete action space, and we are trying to sort of use it for a problem that is rather continuous, right? So basically, the first thing we try to look at is the sampling, right? Before I tell you more about how the MCTS algorithm work itself, right? The sampling is a integral part of the whole MCTS workflow, because you can imagine at higher dimension, right? When you are trying to sort of get new configuration, which are basically like you can imagine each crystal or configuration as a set of vector, right? And you need efficient sampling. As you move towards a higher dimension, right? Your samples tend to become clustered and clustered, right? If any sampling techniques that you use doesn't cover the whole search space, and obviously like your optimization algorithm, that sort of limits your optimization algorithm to sort of explore the space efficiently and getting better solution for your desired problem. So we implemented some of this adaptive sampling like Sobol or hypersphere sampling, right? So they allowed us to like sample the efficient search space efficiently. And there is a parent child also corresponding, which I will come later. But the sampling sort of the first incorporation from our end to this continuous space version of the MCTS. The next one is the depth scaling scheme, right? So you can imagine, right, just a general overview. So when you start, right, for MCTS, it's basically a tree search. That's what pretty much is understandable. And you propagate these branches, right? And as you propagate these branches, you explore the search space more and more. It is expected that when you go deeper down the tree, right, your search is sort of is close to the convergence, right? And so now each node, right, you use each node to explore the areas in the search space, right? You use each node to explore the surrounding areas, right? Now, as you can imagine, right, if we have a like area of sphere of influence around each node, right, as you go deeper, like if we have at the highest depth of the tree, right, if you have a same sphere of influence as the root node, so where we are expecting that the search is almost close to its convergence, it will probably rather delay your convergence because you are forcefully increasing the possibility. So we have implemented this window scaling scheme, right, where we basically sort of scale the sphere of influence where the search will look as the depth of the tree is increasing. So the sphere of influence around each node is gradually decreases. We have different techniques to implement that, but I won't go into those details. But this is the second addition from our group to this continuous space version of the MCTS, right? Now, the question comes, right, we have implemented this modification. How does it work? So we looked at this performance of these trial functions, right, which people use to sort of benchmark any optimization algorithm. I put 3 different categories of trial function, right? So basically like the unimodal, the multimodal, and the fixed dimensional, right? The multimodal where you have many minima, the fixed dimensional, I use like Dijon N5 where you have like this sudden drop in the minima. And if you look at the solution, right, for all of the cases, right, I compared it with particle swarm optimization, which is also a rather popular optimization for this kind of high dimensional problems, right? If you look at the performance, MCTS did perform well, both in terms of speed of convergence and the quality of the solution, right? This further motivated us, right? And a portion of this work was published in Nature Communication. So this sort of motivated us that, hey, we now have an optimizer that works well at higher dimensionality. So can we have a like workflow that is implemented to crystal structure that leverages this benefit of MCTS, CMCTS that we have modified, right? So we came up with this casting workflow, right? So basically, this is a more like general overview of what are the key components of the workflow, right? So the first part is the defining optimizer. So we basically define optimizer. As of now, you probably have guessed it that it's MCTS, right? The second portion is the adding the evaluator. The evaluator, I mean, is right, like when you are dealing with any material system, right, you need a computational package. Like my peer Aditya mentioned in his at the last slide of his talk, right, you need VASP, or you need lamps. So these are like lamps is for is a MD package that you can use to calculate the properties of a material. VASP is for high fidelity quantum calculation. You need to put the evaluator with the optimizer to sort of run. Then you define the objective function. The objective function with the MCTS is something that I'll come in the next slides. But like objective, you need to have something, right, which guides the optimizer. So you have the provision to select the objective. The other side of the defining these key components is, right, which are related to the crystalline system, the system that you are drilling with, right? You can have like a lattice vector range, you can have number of atoms, you can have the chemical composition. Then you sort of select the properties that you are trying to optimize. Then you select, then there is an option to select the output. So during the search, right, in our previous talk, right, the speaker showed up a framework, right? You can visualize how the search is progressing, right? You can select what are the visualization aspect that you want to see in the front end or the software that is in front of you. And finally, the output and monitor, which is basically the platform that will give you the visualization. These are the sub input to the packages, right, which I just mentioned. Moving forward, right, the MCTS, how does the MCTS for crystal structure optimization work, right? So basically, this is in general with the MCTS, any MCTS framework, like whether it's discrete or it's a continuous action space. So the first stage is the expansion stage, right, where you start with a node that is random in nature, right? Like for the crystal structure perspective, we start with an amorphous structure, you can imagine, and we basically sort of expand the tree by sampling, say for this case, 3 new nodes, right? These are basically the child. How do we sample? We use some perturbation, right? This is your sort of parent crystal structure, and you can perturbate the crystal structure, right, by adding one atom or removing atom. You can mutate the lattice parameter, you can mutate the atom position itself, right? This will give you a new child from this parent. Now the thing is, once you have the first expansion stages, right, and you are trying to sort of grow a tree, you need to select one of these nodes, right? How do we do that? This is where the simulation and backpropagation stage comes, right? So basically what we do is, right, we randomly pick one node, right? And we sort of, this is where the Monte Carlo names come from, right? We do some random playouts. We take this structure and we perturb it to generate like 10 or 15 or whatever your number of playouts are, samples that are closely similar to this particular node, right? And we take an objective function. This is what I was explaining earlier, right? We use the UCB policy. So in simpler terms, UCB policy has 2 components to it. One is the exploitation term, one is the exploration term. The exploitation term is, right, what basically guides the reward, like the material system that you are dealing and the property, right? So for an example, we are optimizing the energy. We are trying to get the lowest energetically favorable structure. That would be our energy, right? And we are trying to reduce the energy. So it should be min. I have given max because like most of the time we are trying to say, for an example, if we're using density, we try to increase the value of the density. But this is mostly like it gives you the reward, right? If you sample a configuration, how good it is in terms of whatever property you are looking for. The next part is the exploration part. Now, the thing with the MCTS is, right, you can imagine when we are growing a tree, we are looking at different nodes, right? For an example, it may so happen that like you find a node which are suddenly very good, but when you are doing play out and you are expanding that node, right, continuously, it may not lead you to the desired solution if there is a barrier, right? The defect, you can remember the defect example I showed you, right? You cannot like say for an example, if you try to imagine, right, if you have a defect configuration that is not initially linear in nature, you cannot get to the final defect configuration that is like a whole straight line, right? You would get stuck in between somewhere. Now, if your policy would have been based entirely on the reward, right, it would keep on visiting this node over and over again and search would get stuck. the exploration terms does is, right, it balances out the reward with the visit. So once you start visiting a node, the more and more you visit, right, it value deteriorates, right, like it quality degrades, because like those node in the further expansion won't give you a good child, and the MCTS would look for another alternative. This helps to jump from one node to another node, and this is sort of an advantage for MCTS to get past those barriers which are like hiding your metastable polymorphs somewhere in your optimization surface, right? And yeah, once you do the rollout, you can sort of take the aggregation of the rollout values, and you can get a decent score for each node, right? And based on that, you use UCB policy, you recalculate all of the objective values for each node, and you do further selection. Another crucial aspect of it is back propagation, right? Now, when you do the playout, right, you are sampling newer and newer members, and this quality of the node, you are getting more insights into how your node qualities are, and you need to update your whole tree, right? So this is where the learning comes from, sort of learning. So we sort of back propagate this knowledge throughout the tree, right? And now the next version of the tree, if you have a Markov process, right, in the next step, when you move to the first step to second step, right, your whole tree knows, right, how the previous step, what are the best possible qualities of the node based on whatever playouts or sampling that you did so far, right? This sort of helps guiding the search towards convergence more efficiently. The final stage is like selection and expansion. Once you have the back propagation, you select a node based on the current best value of your UCB score, and you expand it more, and you go downwards and downwards. Also, we need to remember that at the same time, we are implementing this depth scaling policy, right? Continuously, sort of reducing the search area around this crystal. And this, you can imagine, every time you do that, right, this generates a crystal structure. Because basically what we are dealing with, it's atom like crystal structure, which are like basically composed of atom, and they are just basically XYZ coordinates, right? And this is the basic flow chart of the MCTS diagram, right? So like you start with a random relaxed configuration, you have a root node, you expand, you back propagate, you select and expand until you converges, we run the loop. Now we have applied the casting workflow for many crystalline systems. The target was to check speed, scalability, convergence, and what are the transferability, right? So we took different system, right, at different scales and different dimensionalities, and tested how casting with MCTS workflow, of course, performs and how their performance is compared to its like other optimization algorithms that are generally being used, right? So the first one was carbon. Obviously, like many of us are familiar with carbon polymorphs. It has like probably the most polymorphic diversity. So we took MCTS. So the first one, we tried to sort of look at this convergence speed, right? We took MCTS genetic algorithm random to sort of converge to the graphite, which is like more stable polymorph, right? I'm not sure whether you can see it or not, like if the graph is visible, but if you look closely, right, the casting with MCTS, right, converges to a better solution more faster than genetic algorithm or the random sampling for this case, right? This is like an average of 4 or 5 independent trials, right? And the overall convergence speed and the solution quality is better. In the right, you see the different metastable polymorphs, right, that were sampled during the casting. This is a basically isomap plot for the metastable polymorph. So basically, I used a descriptor, which I mentioned in the first slide, right, and I did a PCA principal component, and this each point here is a crystal structure that is sampled at different temperature and pressure with the casting workflow. So the polymorphic diversity it sort of gets because we managed to recover the known polymorphs such as hexagonal diamond, graphite, cubic diamond, stacking disorder, and a few other known polymorphs as well. The next application was to test its scalability, how it performs as we increase the size of the system, right? The first thing we did was we took this silver unit cell, right, and we tried to see like how it converges. So again, MCTS did better than the random which was sort of expected. Now we increase the size of the unit cell, right, to 32 atom, to 108 atom, and 256 atom. 256 atom, you can basically imagine it's equivalent to 771 dimension, because like each atom has 3 coordinates, right, in Cartesian system, x, y, z, and if you multiply it with 3 and 6 lattice parameter, a, b, c, alpha, beta, gamma, that will give you 771 dimension, which is quite a high dimension. And if you look at the solution, right, for each of the cases, MCTS got a very good solution. It managed to reach the FCC structure, right, which we know the solution, like best energetically favorable polymer for the silver system. The next we looked at, right, is like a 0-dimensional system, which are clusters, right? So for clusters, right, there is this certain chain cluster, right? And one of these is going to be a demo from my end. So like I'll show you how you can use casting to get this certain chain gold 13 atom cluster. You see, this is an icosahedral structure, right? And we use the casting for different sizes, right? And another thing is we know the solution, right, for the each of these sizes, this certain chain cluster, because people have used certain chain potential and different algorithm to find this cluster configuration in their earlier work. So we are looking at whether MCTS converges to those or not, and it successfully managed to converges to the final configuration, both structurally and energetically, which are similar to the known global minima of this 0-dimensional system, right? We further looked at 2D system, right? This 2D system, the first one is the graphene, which is basically a CH polymorph. So like we used casting, and casting sort of also converges to the graphene. We used hexagonal boron nitride with like a physics-based potential model as a like evaluator. And it also managed to get the hexagonal boron nitride, which we know, right, for 2D system, hexagonal boron nitride is a global minima for this particular system, right? Finally, we did an interesting application with casting, right? So basically, like you have this record perovskite nickelets, right? The neuromorphic computing is something that is in the trends right now, right? There have been a lot of effort in research for developing better memory stir, right? And the perovskite nickelate, they have these properties, right? They can switch from metal to like semiconductor to insulator, right? The thing is, right, when you dope like perovskite nickelate, right, with hydrogen, so for some of the doping concentration and some of like a few particular position of the hydrogen atom, right, it gives you structures where you see, right, the density of states near 0, right, it disappears. So like there is a transition happening from semiconductor to metal. This is particularly applicable for neuromorphic computing, right? Excuse me. So basically we use casting, right? And we try to look at different metastable configuration, right? At different hydrogen doping concentration. We found that for a doping concentration of 1H, you start to get this metastable polymorph, which showed this transition. This work was the polymorphs was synthesized and put in a device by one of our collaborators at Purdue, and this work was published in Science. And further, this data was used to sort of like for another publication at Nanoletters. But this sort of shows, right, like for the applicability of casting framework for a different wide range of application, right? This is not exactly a crystal structure search, but casting did perform well in this particular case of problem as well. Now, with that, like I would conclude with the applications part, right? And like we said, this is a tool that we have been developing at CNM, right? And we do have a prototype. So I just tried to give some brief look on the prototype, what we are developing. This is basically the front end. The back end code we already have, which is perfectly working, and which we have used it so far for the different sets of applications, right? So the front end codes, right, like where you have a like job dashboard, right, and you can create a new casting job. Then the first page, right, where you can give the properties, the target properties. You can either do structural search or component design. You can select the plugin, which are basically the evaluator. You can upload different scripts. So for an example, right, if you use like VAS for lamps, right, they have their individual script. Those of who are not familiar, right, this molecular simulation tool, right, so they have their own scripting language, and you can sort of have the script to do the put the commands that you sort of want to be evaluated during the search, right? You can upload the script, you can select whether minimize and maximize, you can select the property, then you can give the crystalline system the bounds of the lattice parameters. And you can sort of select all these parameters. Then you select the objective function. So as of now, whatever I have showed you, right, those are based on energy, and those were like a single objective. You can have multi-objective also. Say you are trying to maximize density and minimize energy. You are trying to find a polymorph which are stable, also like high density polymorph. So you can have multiple objective with individual weights, right? And the C is an exploration constant in the UCB, which I haven't mentioned earlier. This basically guides the exploration part of the UCB itself. You can select the uniqueness function, right? Also, like one thing I would like to mention here is that this uniqueness function is necessary because for crystal structure search in particular, right, when you sample a lot of different sort of crystalline polymorphs, right, you tend to sample a degenerate configuration, which is not very much acceptable as far as the searches are concerned, because the for some of this evaluator, right, the quantum calculation evaluator for FAST as an example, these are costly to perform one calculation, and we would not like to waste one particular calculation for sampling a polymorph that is similar. So we sort of apply a little bit of penalty in the reward part, right? Multiply it with a uniqueness function. So it basically tells the search if it is for a particular, on a particular node, right? If it is sampling a polymorph that is not different in nature, that node is not a good one. So you can select those, there is SOAP, there is MBTR. So these are basically like the descriptor packages that are available in Python as a libraries. Now you see a final sort of page where the summaries of the option that you have selected so far, and you can just go ahead and submit it as a job. You can monitor how the job is evolving, and you can also monitor how the tree is evolving, right? At each node, what is happening, what are the structures, right? And we do have a pseudocode that is available for casting. So this is as a reference to this paper. I do recommend you, if you are interested, check out this paper. And the repository is publicly available. So I would use this repository to give you a demo how to use the casting packages. So I mean, if you are interested, you can just right now you can go to the repository and like follow up with me with the demo itself. You can run it basically in your computer. It will run in Google Colab. You just need to have a like Google account. That's it. And yeah, this is the repository. Let me know if you, I can put it in the chat as well if you are interested in going to the repository and run it yourself while I give the demo. And that's pretty much it from my end. Now I'll just move towards the demo section. So before moving to the demo, so I'd like to ask if you have any question, you can ask me right now or maybe at the end of the talk.
Thank you so much, Suvo. Any questions for Suvo? Otherwise, he will actually move forward with the demo. Okay.
So this is the repository that I was showing you, right? And it's available. So I'll just give you a brief on the repository. So like, so this is basically the supplementary for the casting paper. You can find the link to the paper here. These are the things that we have discussed so far, right? You have like some prerequisite packages. One thing is, right, we have used so far the LAMPS, and the LAMPS Python integration is kind of necessary to run this job. And the details you will find in the LAMPS website. But for this particular demonstration, I will use AAC for the structured energy calculation, because like LAMPS sort of doesn't support in the Google Colab, and its Python interface is a bit complicated to handle. right? You have the installation code, how to install. You can run the code. So basically, like I'll just give you a brief demo. This is also available in the Jupyter example that I'll show you. But so basically, you install the pip install the package, casting package. You import casting. So you import different function like utilities function, right? You have a perturbation function, you have a lamps evaluator function, which basically that calculates the energy, and you have to generate a random data for the root node, right? You seed it with the structure for the reproducibility, right? And you have initially you define the crystalline system where you have, for say, I'll be doing the gold example, right? For the gold example, right, you need to mention the minimum interatomic distances and the maximum interatomic distances of the atom, the box size, right? Then you have to tell the search the constraint, right, for the number of atoms, right? The lattice parameter here for the clustering system, there is no lattice parameter as such, it's the box dimension. So we'll be using a uniform box dimension 50 by 50 by 50 cell. Right, then there comes a perturbation move, right? Remember, I showed you some sampling techniques, right? Here we use the hypersphere sampling techniques. For that, you need to mention some perturbation parameters like maximum mutation. Then for lamps, there are some parameters, right? It's the lamps accept some pair style, pair coefficient. Once you mention that, you basically first create a root node data, right, with the create data function. Then you define the perturbation, initialize the perturbation function. Then you initialize the evaluator, and you basically call the MCTS with all the parameters, right? The MCTS has different parameter itself, right? Which I explicitly didn't mention before. But as you can imagine, when you are growing a tree, right? One thing I mentioned, that is the playouts. Number of playouts can be one, which is you see here. Then another is the simulation, number of simulation you want to do. The head expansion, when you are first branching out from the root node, right? That is also a parameter. So you mention all these parameter, number of iteration, and you just launch the code, right? We have some examples in the repo. This is what I'm going to show you. And we have a data set available for the carbon metastable polymorph, right? Now, moving back to the demonstration, right? Let me move back to the. So in the repository, you will find a link that is open in Colab. You just hit the link. So this will open typical Jupyter notebook in the Colab, right? So the first thing that we are going to do is that install the casting. I have already installed it, so I don't need to run this block. So you can, if you are trying it right now, you can run this. Then we need the potential file. We'll just copy the potential file from here. Just a second. In here, from the repository itself. It will show up in the left side. It takes a little bit time just to update the GUI. Then we import all the packages, right? Okay, I think I got to install it again, most likely. Just bear with me for a few minutes. So by that time it installs, right? Let me give you a brief into that. So like I showed you the example, we'll importing the module, right? We'll set the seed. It's the similar example that I just showed you, right? We'll define the constraints. We'll create one random data and we'll save one initial configuration, whatever random structure that we are using, right? To show just for your visualization. We define the perturbation, we launch the MCTS. Once the MCTS runs, right, we'll have like a generated set of structure, particular structure that is the global minima. We'll write it in a file and we'll see the final configuration. This is for 13 atoms, so you will see the icosahedral structure as the final optimization version. Okay, I think it's installed now. Hopefully I'll be without any error. I'll be able to import the modules. Okay, it's showing the same error. I think just give me a second. I have another collab link that. Oh, I remember I need to update the runtime. It was after installation probably. Start running. Yeah, it worked. Okay. I just had to like restart the runtime. When you install something, you have to like sort of restart it. Now you defined it, you created the random data. Now we just saved it in a postcard format. Just hold on for a couple of seconds. Once it comes, I'll show you this how the initial structure look like, where we're starting from. That's basically the root node, right? Yeah, it came. Let me just download this structure. I'll share my visualizer screen again, where the structure, you can visualize the structure. Just a second. Yeah, you see this structure. This is a 13 atom initial structure. It looks pretty much random, right? There's no symmetry and nothing in it, right? Now what we will do, we will go ahead and run the casting optimizer with the MCTS optimizer, and we'll look at how the final configuration look like. Again, just to remind you, this is like 13 atom. So the final configuration, we are expecting to get an icosahedral structure. Now coming back to the POLYBOT, right? Let me just define the perturbate, and let me just launch the calculation. It should take a couple of seconds, a minute or so for it to complete. You can observe the total number of evaluation and the best score yet, right? As it is, because the energy is the score. So it's being calculated as each of iteration is being done.
Optimization in real time.
I'm sorry.
I just said optimization in real time.
Yeah. Yeah, it converged. So just a second, it's almost done. Yeah, now it's done, right? We'll take the final configuration and we'll save it in a file that is named as 0.postcard. So it will sequentially let it come in the left side. It should take some time, like a few seconds to for the file to show up in GL. Yeah, fine. Okay. So one thing I'd like to mention during your run your search, right? You generate this dump file.dat where you have this crystal structure parameter and corresponding target objective value saved, right? That's like crystal structure parameter in the sense the lattice dimension, which we took 50, 50, 50, and the Cartesian coordinates, the fractional coordinates. You can sort of use this dump file to sort of generate the structures that were sampled during the search itself, right? And if we just download this structure, right? And let me just share my screen again, the window. Just give me a second. You see, right? This is the initial configuration that we started with, and this is the final configuration. This is a complete icosahedra. So this is basically like a demo example of the casting. Again, I would like to mention you, right, that this is merely a pseudocode with very limited capabilities. It doesn't incorporate many of the modification that we done for demo purposes. If you are interested, you can like contact my supervisor, Dr. Subramanian, me, or for the more details on how to use the code. And with this, like I'd like to conclude my talk, and I'd be happy to take any question if you have. And yeah, feel free to use the repo on or see the paper. The paper has more elaborated description on whatever example that I have showed you. If you have any question, feel free to reach out to me again. And thank you.
Thank you so much, Suvo. Questions for Suvo or for Aditya? You can unmute yourself and ask the question, or you can type it in the chat. Either ways is fine. Or you can try out his example problems and reach out.
Yeah, you can just log into that GitHub repository. For your reference, I can just paste the link in the chat. Please feel free to go there and look at the example. I think it's pretty straightforward to run. Yeah, and do let me know if you have any question. Thank you.
Yep, we'll be available here for the next few minutes. If you have questions, feel free to ask. If you have any questions for Michael on carbon or getting access to carbon, you can actually ask Dr. Sternberg as well. All right, let's thank all the speakers if there are no questions, and then we will come back again in the afternoon session, starting with the description and capabilities of POLYBOT. So Dr. Henry Chan would basically be chairing the session in the afternoon. Thank you so much, everyone.
Thank you, everyone.
Can Henry Chan be made co-host again?
So first, I'll be going over the STEM mode of the software. As I mentioned, this is STEM and TEM images are used to take pictures of grain boundaries. And to better understand these, the Ingrained software was designed. First, it queries materials databases in order to gain information about crystal structures. It then creates a register between the crystal structure or crystal structures to form the grain boundary. It registers this grain boundary against the experimentally observed image, and then optimizes a variety of parameters until you converge upon a experimentally informed grain boundary structure. I'm going to go over the example of how this software is used for the NMC 622 battery material. This is a cathode material that is used in lithium-ion batteries. It offers a high capacity at high voltages and so is of great interest. However, over a few charge and discharge cycles, the properties degrade significantly. This is due to irreversible oxygen evolution. And so the question ended up becoming, are the grain boundaries responsible for this? There are two kinds of grain boundaries. On the bottom image, I have 3 grains shown. On the bottom highlight is a high angle grain boundary, where the top one is a low angle grain boundary. This is further zoomed into on the right, where we have the orange guiding lines showing the bottom grain and the top grain and where they meet in the middle. So the challenge for Ingrained was first to identify the structure of the grain boundary, and then follow it with density functional theory calculations in an attempt to explain the oxygen evolution in the system. So to run Ingrained, the first thing you need is a TEM image. If you don't have an experimental image to match against, then the framework of matching to an experimental image isn't going to function. On the left here, I have the experimental TEM image of the grain boundary for the cathode material. You see here the grain boundary forming a tilt right there. You need to provide some input parameters for your material. What is the HKL projected into the screen? What's the HKL projected vertically in the image? What's the angle of the top grain from that vertical HKL? And what's the tilt angle of the bottom grain from the HKL? With this information, the Ingrained software queries the materials project database for crystal structures that match the composition and symmetry of the material that you use as input, and then selects the most likely candidates to form the grain boundary. Afterwards, the grain boundary is constructed, a HADF STEM image is generated. This is registered against the experimental image, and then a variety of parameters are optimized automatically in order to improve the consistency between the experimental and theoretical images. After a series of optimization, you end up with an overlap of the experimental and theoretical images, and you see that the theoretical image here is a pretty good match. So now we have a grain boundary for the crystal structure. After obtaining that, further calculations can take place. What was done was relaxation using density functional theory, which found that there were 1D channels forming in the highly lithiated cathode state. The oxygen evolution occurred over charge and discharge cycles, and so a low lithiated state was calculated for the same material, and the stability of oxygen in these states was identified. The first observation was that oxygen was more stable in the bulk of the material than at the grain boundary. And second, oxygen was more stable in the fully lithiated cathode material than the low lithium cathode material. In fact, vacancy formation energies decreased in the low lithiated states, resulting in the oxygen evolution that was occurring in the charge and discharge cycles. As the cathode went from high to low lithium content, the oxygen vacancies formed, oxygen evolution occurred, and even when you made it lithiated again, the oxygen had already been lost, and you had an overall decrease in properties. So this is an example of ingrained STEM being used in order to further investigate an experimental system and provide an explanation for experimentally observed phenomenon. Now, the experimentalists can work to try and minimize the presence of these grain boundaries in order to prevent this oxygen evolution from occurring. So, successful application of Ingrained. Now I'll be going over the STM mode. This is used to characterize surface structures. What an STM measurement actually does is it measures at a certain bias voltage the charge density at the surface of your system. It is important to note that it doesn't actually measure the exact atomic positions, it's measuring the charge density. So what can appear as a raised feature on the STM measurement could actually be a recessed feature with a raised charge density. Similarly, you could have a raised feature where the charge density sits closer to the atomic surface, which would show up as a recessed feature on the STM image. So it's not quite as simple for interpreting these images as saying that this is an atomic position, this is below the top layer, this is an atomic position, and so forth on. It's more complicated than that. So the Ingrained software was further developed in order to take an STM image, have a candidate surface structure, simulate that STM image, optimize over a variety of parameters, and create a register between the experimental and theoretical images in order to say with better certainty what the surface structure actually is. So the way this actually works is by taking advantage of the fact that a tunneling current correlates to the electron density. So if you perform a DFT calculation and write the partial charge density at the bias voltage that the STM measurement was taken at, then you can plot an isosurface using the Tursoff and Hammond approximation to approximate what the STM image would look like. This requires two inputs. The surface structure itself, you need to actually have a surface in order to, or a material system in order to generate a charge density. And then the partial charge density local to where we approximate the STM measurement took place. On the left here, I have shown what our simulation cell looks like. So we have our STM block here with our surface material and our substrate. You have your charge density. You plot an isosurface from that charge density plus a tolerance on what's actually being represented. You decide how far below the surface you're going to plot that isosurface, and how high above this surface you're going to plot that isosurface. Using these parameters, you generate a theoretical STM image, which is great. It's very pretty. But on its own, it means nothing. There are several parameters in what I just listed that can be tuned to say nothing of the rotation of the image relative to the experimental register, stretching and shearing that could occur, those sorts of skews in the experimental image that need to be replicated in the theoretical image. So Ingrained STM optimizes these parameters in an automated fashion. In the top here, I have several STM images taken for the borofane surface. And on the bottom here, I have those images registered against the experimental structure. You see, as Ingrained optimizes the parameters, it converges, or it starts with a pretty not so great guess, but eventually converges on what looks like a pretty coherent match between the STM experimental image and the STM simulation image. Now, I mentioned that the example being shown there was borofane, and this is of importance because borofane is a 2D material with potentially very good properties, but it's prone to oxidation and just general degradation of properties when it's removed or when moved from ultra high vacuum to atmosphere. So the goal was to passivate borofane using hydrogen to prevent the evolution from or the oxidation from occurring, transfer the borofane to another environment, put it in ultra-high vacuum, and then heat off the hydrogen atoms. STM images were taken by experimental collaborators along with a variety of measurements of the thin film that was generated. And so the first question was, where's the hydrogen actually located? There were three possible scenarios. One where the hydrogen was located on top of boron atoms, one where it was sitting on a bridge site between boron atoms, and finally where it's sitting in both positions. Hydrogens exist at both positions. The best fits for the three scenarios I outlined are shown here on the bottom, and the 2H structure where hydrogen sits at both sides simultaneously ends up having this ladder dimer-like structure, which is a good register against both the 100 millielectron volt and 24 millielectron volt images. So after this was done, a surface structure was identified. Further calculations took place to further match the experimental measurements taken, and eventually a science paper was published on this borophane material, which successfully passivated the surface and prevented oxidation from occurring in atmospheric conditions. So I've gone through a successful example of Ingrained STEM and Ingrained STM. I just want to discuss a little bit more in depth of the software now. Specifically, Ingrained, when it's optimizing its parameters, is solving a local optimization problem. So depending on your starting parameters, you might converge onto different minima in your optimization process. On the bottom here, I have for the same partial charge density, the Ingrained optimizations against an experimental image for 4 different starting points. On the left here, we have a wiggle with a fairly consistently colored band throughout. Next, I have bands of a consistent color that increase and decrease in thickness. Then a more atomically resolved wiggle pattern. And finally, bands of approximately consistent thickness all the way through. These were all from the same initial partial charge density again, but they had different starting parameters. And this was done by using the built-in multi-thread approach to the software. What this allows is that the user provides a starting point for all of the calculations to be centered around, and then the Ingrained software will run optimizations around or for several sets of parameters centered around the input values. Here is a box and whisker plot for another system that I performed. On the x-axis are various structures. On the y-axis is the figure of merit. Lower score is better because that indicates less mismatch between the experimental and theoretical images. And you can see that there are some cases where you have a fairly wide spread of scores and some cases where you have a fairly narrow